Hello everyone. In this video we are going to discuss about chemical engineering GATE 2019 chemical reaction engineering questions with solution. GATE 2019 question paper and the answer key link is available in my description box. You can download it. Question number 47. The elementary liquid phase irreversible reactions. A gives B gives C. So K1 0.4 minute power minus 1, K2 0.1 minute power minus 1. Takes place in an isothermal ideal CSTR. Constant temperature, continuous Triton reactor. Pure A is fed to the reactor at a concentration of 2 mole per liter. So the concentration Ca naught is equal to 2 mole per liter. For the residence time, that is tau, that maximize the exit concentration of B. Exit concentration of B means that is Cb. The percentage yield of B defined as net formation rate of B by consumption rate of A into 100. Objective of this question is to determine the percentage yield of B by using this expression. After calculating the percentage yield of B value, we have to round off the result to the nearest integer. Data. First order reaction. A gives B gives C. Rate constant K1 and K2. K1 is equal to 0.4 minute power minus 1. K2 is equal to 0.1 minute power minus 1. Ca naught, that is initial concentration, 2 mole per liter. So residence time, that is maximum Cb. Objective of this question is to determine the yield of B by using the expression the ratio between net formation rate of B to consumption rate of A. Solution part, yield B is equal to net formation rate of B divided by consumption rate of A into 100. So here Cb by Ca naught is equal to K1 tau by 1 plus K1 tau into 1 plus K2 tau. This is K2. K2 tau. So tau max formula 1 by root of K1 into K2. K1, K2 values are known. Substitute here. Find out the tau max. Tau max is equal to 5 minutes. So here we want Cb value. So this is the maximum value Cb. So here substitute Cb, Ca naught, K1 tau and K2. So Cb is the unknown. So Cb divided by Ca naught value 2. So here K1 is a 0.4. Tau is calculator value 5. Divided by 1 plus K1 is a 0.4 into tau is a 5 into 1 plus K2 is a 0.1 into 5. Finally Cb value is 0.88. This is a maximum value Cb. So yield B. Yield B, this is our objective. Yield B is equal to net formation rate of B, that is a numerator. Net formation rate of B. So from this reaction A gives B gives C. Net formation rate of B means K1Ca minus K2Cb divided by consumption rate of A K1 into Ca into 100. This is the equation for yield of B. So in this equation we want K1, K2, Ca, Cb. Then only we are going to calculate the yield of B. So we know K1 and K2 Cb value. We don't know the Ca value. How will we calculate the Ca value? So in CSTR performance equation, tau is equal to Ca naught minus Ca by minus Ra. So here Ca naught minus Ca by minus Ra means K1 into Ca. So here tau value already calculator value we should take 5, that is equal to Ca naught is given to Ca is a unknown divided by K1 values are given data 0.4 into Ca. So they cross multiply this one. 5 into 0.4 into Ca, that is 2 Ca. This minus Ca comes to this side plus Ca. Totally 2 Ca plus 1 Ca, 3 Ca. So in RHS side this is equal to 2. Okay. From this Ca is equal to 0.66. So now we get Ca value. Substitute in this expression. Yield of B expression. So yield of B expression K1 into Ca minus K2 into Cb. This is the numerator part. So K1 is a 0.4. Ca is a calculator value 0.66 minus K2 is a given data 0.1. Cb is a 0.88. So denominator term K1 into Ca. K1 is a 0.4. Ca is a 0.66 into 100. So finally we get 66.66 percentage. So the round of this value, yield of B is equal to 67 percentage. So answer for this question is 67 percentage or 67. So answer range is given 65 to 68. Our answer within this range. Okay. Next question. Question number 48. The elementary irreversible gas phase reaction A gives B plus C is carried out adiabatically in an ideal CSTR continuous steady tank reactor operating at 10 atmosphere. P is equal to 10 atmosphere. P or A enter the CSTR at a flow rate of 10 mole per second. This is molar flow rate. And a temperature of 450 Kelvin. This is T1. Assume A, B, C to be ideal gases. The specific heat capacity at constant pressure Cpi and heat of formation Hi naught of component A, B, C are given. Cpa is equal to 30 joule per mole Kelvin, Cpb is equal to 10 joule per mole Kelvin, Cpc is equal to 20 joule per mole Kelvin. Similarly, standard heat of formation, that is delta, here H naught A is equal to minus 90 kilojoule per mole, Hb naught is equal to minus 54 kilojoule per mole, Hc naught is equal to minus 45 kilojoule per mole. These are the heat of formation value. The reaction rate constant K per second 0.133 exponential of E by R into 1 by 450 minus 1 by T. K is equal to K naught into E power minus E by RT. Okay. So this is the expression. So in this expression we are going to calculate the K value. So here E is equal to 31.4 kilojoule per mole. Universal gas constant R value. So R values are given in different unit. So one unit is a atmosphere unit, another is a joule per mole Kelvin. So atmosphere unit is 0.082 liter atmosphere per mole Kelvin, another unit 8.314 joule per mole Kelvin. The shaft work may be neglected in the analysis, and the specific heat capacities do not vary with temperature. All heat of formations are referenced to 273 Kelvin. This is a reference temperature, 0 degree Celsius or 273 Kelvin. The reactor volume in liters for 75% conversion is. So conversion is a 75%. So objective of this question is to determine the reactor volume in liter. After calculating the reactor volume, we have to round off the result to the nearest integer. Okay. Data. So given reaction A gives B plus C. This is adiabatic reactor. Pressure is equal to 10 atmosphere. Molar flow rate. So given 10 mole per second. T1 is a 450 Kelvin. So different Cp values are given. Heat of formation values are given. So we have Cpa 30 joule per mole Kelvin. Cpb 10 joule per mole Kelvin. Cpc 20 joule per mole Kelvin. Heat of formation for A, B and C are minus 90, minus 54 and minus 45 kilojoule per mole. So here rate constant is directly not given. So the equation is given, K is equal to 0.133 exponential of E by R into 1 by 450 minus 1 by T. So here E values are given, activation energy. So the E value 31.4 kilojoule per mole. So the kilojoule is converted into joule. Why? Because all these values are in joule. So that's why this is converted into joule. So here 31.4 into 10 to the power of 3 joule per mole. Okay, this is the activation energy. So the capital R, that is gas constant values are given in different unit. So atmosphere unit we should take 0.082 liter atmosphere per mole Kelvin. So joule we should take 8.314 joule per mole Kelvin. So the heat of formation reference temperature 0 degree Celsius or 273 Kelvin. So the conversion XA is equal to 75%, we should take 0.75. Objective of this question is to determine the volume value in terms of liter. So adiabatic CSTR. So the conversion equation Cp dot into T2 minus T1 by minus delta H reaction minus of Cp double dash minus Cp dash into T2 minus T1. So in this expression Cp dash is equal to specific heat of reactant. Cp double dash is equal to specific heat of product. T1 is a 450 Kelvin. Okay. So we want delta H reaction value. This is the unknown. T2 also unknown. By using this expression we are going to calculate the T2 value. But one more unknown is here, that is a standard heat of reaction. So any method is available to calculate the standard heat of reaction? Yes. So in our problem we have standard heat of formation value. So by using the formation value to determine the standard heat of reaction value. So what is the formula? Delta H reaction is equal to summation of standard heat of formation of products minus standard heat of formation of reactant. So in this problem we have standard heat of formation value. So our reaction is A is a reactant, B and C is a product. Am I clear? So here A gives B plus C. So product is a 2 product, reactant is a 1 reactant. So by using these standard heat of formation of product mean we have only 1 is right, only 1 reactant, 2 products. So here we should take B and C is a product, is right. B and C value, B value minus 54 minus 45. This is the standard heat of formation of products. This minus value is already given, you don't worry. Minus 54 the data is given, minus 45 this data also given. Minus of standard heat of formation of reactant. Reactant is we have only 1 reactant, that is capital A. So we should take that value minus 90. So finally we get standard heat of reaction minus 9 kilojoule per mole. So the kilojoule is converted into joule, 9000 joule per mole. So this is a standard heat of reaction, that is delta H or XL. So the XA equation, what is the XA equation here? XA is equal to Cp dash into T2 minus T1 by minus delta H reaction minus of Cp double dash minus Cp dash into T2 minus T1. So here what is a Cp dash? Already I said Cp dash is a specific heat of reactant. We have only 1 reactant na, that is A value, Cp A value 30. We should take 30. Into T2 is unknown, we are going to calculate the T2. T1 is given 450, substitute here. So here delta H reaction minus 9000. Already in equation itself we have one minus na, minus of minus 9000. So minus of Cp double dash is a specific heat of product. We have the 2 products now, one is a B, another one is a C. So 10 plus 20, that is addition. Minus Cp dash. Cp dash is a specific heat of reactant, that is a 30. Into T2 minus T1, T2 is unknown, 450 is a T1 value. So here in numerator part 30 into T2 minus 450 whole divided by. So here 30 30s are cancelled. This is plus 30, this is minus 30. That is 0 na. So this term you don't worry. So here minus it minus plus 9000. So here what is XA? XA is a 0.75, 75% conversion. Substitute all the value, rearrange this expression, finally we get T2 value 675 Kelvin. We want K value na. So the K equation is given. K is not directly given. K equation is given. Arrhenius equation. K is equal to 0.133 exponential of E by R into 1 by 450 minus 1 by T2. So in this expression 0.133 exponential of E values are given. We should take 31.4 into 10 to the power of 3 whole divided by 8.314 into 1 by 450 minus 1 by 675. So after substituting this value, what is a K here? K is equal to 2.180. That is the rate constant value. For CSTR, so what is the performance equation? V by V naught is equal to CA naught minus CA by minus RE. So in this expression, CA naught into XA by minus RE. We should take this equation or this equation. So tau is equal to V by V naught is equal to CA naught into XA by minus RE. CA naught into XA divided by minus RA is a K into CA. This is a first order reaction. So here this is gas phase reaction. Irreversible gas phase reaction. Tau is equal to V by V naught is equal to CA naught into XA is a numerator term. Denominator K into CA. What is the CA here? So the gas phase reaction CA naught into 1 minus XA by 1 plus epsilon A XA. What is the epsilon A? Epsilon A is a fractional conversion. How to calculate the epsilon A value here? Epsilon A is equal to stoichiometry of product minus stoichiometry of reactant divided by stoichiometry of reactant. So here we have A gives B plus C. So only one reactant, two products. So stoichiometry of product mean 1 plus 1. 1B, 1C, 1 plus 1 minus stoichiometry of reactant 1A, that is 1, divided by stoichiometry of reactant 1. 2 minus 1 divided by 1, that is equal to 1. So epsilon A in this case equal to 1. So here CA naughts are cancelled. This is a common term. So finally V by V naught is equal to XA mean 0.75. K value, calculator value 2.180 into 1 minus 0.75 divided by 1 plus epsilon is 1 and XA is 0.75. Finally we get V by V naught is equal to 2.411. So this is the equation. So V by V naught. But if we want a V value, how will we calculate the V value? But here V naught values are not directly given. Volumetric flow rate. So instead of that, in question itself given molar flow rate. Molar flow rate in terms of mole per second is right. So that's why we should take volumetric flow rate is equal to molar flow rate divided by CA naught. So here molar flow rate is known, CA naught is unknown. How will we calculate the CA naught value? CA naught formula P by RT. So P is the pressure, that is 10, R is a 0.082 into T value 675. This is a calculator value. This is the outlet temperature. So here we could check the unit. P units are atmosphere. Here numerator is atmosphere. 0.082 atmosphere liter divided by mole Kelvin. So mole Kelvin goes to numerator part. Temperature is a Kelvin. Which one is a cancel here? Atmospheres are cancelled. Kelvins are cancelled. Finally we get mole per liter. So this is the concentration unit or CA naught unit. So after substituting this value, finally we get 0.181 mole per liter. This is a concentration. Now we are ready to calculate the volumetric flow rate value. Molar flow rate is given, that is 10 mole per second. That is 10 divided by CA naught is a calculator value. We should take 0.181. So that is mole per liter. So numerator is a mole per second. Denominator is a mole per liter. So moles are cancelled. Finally we get liter per second. So this is a unit of volumetric flow rate. 55.248. So now we have V naught na. Already we have relation. V by V naught is equal to 2.411. So V naught is known here. 55.248. Multiply here. V is equal to 55.248 into 2.411. So here what is the V? V is equal to 2.411 into V naught na. So 2.411 into V naught values are calculator value, substitute here 55.248. Finally we get 133.20 liter. So this is round off to nearest integer 133 liter. So answer range is given 131 to 138. Our answer within this range. Am I clear? So this is our objective. So volume of the reactor here 133 liter. Next question, question number 53. Consider the reactor separator recycle process operating under steady state condition as shown in the figure. The reactor is on ideal CSTR, ideal continuous stirred tank reactor, where the reaction A plus B gives C occurs. Assume that there is no impurity in the product and recycle stream. Other relevant information are provided in the figure. Refer this figure. The mole fraction of B, that is XB, in the reactor that minimize the recycle rate. So the XB minimize the recycle rate. So objective of this question is to determine the XB value. After calculating the XB value, we have to round off the result to 2 decimal places. Refer this diagram. Pure A and B. So A plus B gives C. This reactor is a CSTR. Volume is a 10 meter cube. So here A plus B and C plus C. These 3 are sent to the separator. So here AB recycle. So these values are minimum. Okay. So minimum. This is minimize the recycle rate. So this is maximum. This is the product. Here rate of reaction is given 10 to the power of 3 XAXB kilomole per hour meter cube. Product C, the molar flow rate is given kilomole per hour. By using this data, we are going to calculate the XB value. Data, reaction is given, A plus B gives C. No impurities in the product and recycle. Volume is a meter cube. Rate of reaction R is equal to 10 to the power of 3 XAXB kilomole per hour meter cube. Rate of formation of C, that is 100 kilomole per hour. XB is a minimize the recycle rate. So objective of this question is to determine the XB, that is a mole fraction of B. This is minimize the reaction rate or recycle rate. Molar flow rate is equal to rate of reaction into volume. So here we want kilomole per hour, but rate of reaction in the unit of kilomole per hour meter cube. This is multiply with volume. Volume is a meter cube. Meter cubes are cancelled. Finally we get kilomole per hour. This is the first equation. So rate of reaction 10 to the power of 3 XAXB. Volume is a 10 meter cube. 10 to the power of 4 XAXB. This is equation number 1. What is the molar flow rate here? Molar flow rate is given 100 kilomole per hour. Refer the diagram. This is equation number 2. So both are equal now. Molar flow rate equating equation 1 and 2. 10 to the power of 4 XAXB. This is a equation 1. Equation 2 is a 100. From these, what is the relation XA and XB? XAXB is equal to 100 divided by 10 to the power of 4, that is 0.01. XA is equal to 0.01 divided by XB. So addition of mole fraction always equal to 1. We have the two reactant, one product, na totally 3 components, na XA plus XB plus XC equal to 1. So here XA in terms of XB 0.01 divided by XB plus XB plus XC is equal to 1. From these X is equal to 1. This value comes to this side minus 0.01 divided by XB minus XB. So this is the XC value. So here maximum C. Maximum C means differentiation of XC with respect to XB equal to 0. So this equation is a XC equation. This equation differentiate. So XC is equal to 1 minus 0.01 this xb goes to numerator, xb power minus 1 minus xb. Differentiate this expression with xb. First term 1 is a 0. This is a constant term. So here x power minus 1, n into x power n minus 1. This is a differentiation formula, x power n. So here xp power minus 1, 0.01 is there, minus 0.01 into n into minus 1, x power xb power n minus 1, minus 1 minus 1 minus 2, xb that is 1. So here maximum C mean this value dou xc by dou xb equal to 0, that is equal to 0.01, minus into minus plus 0.01, xp power minus 2 minus 1. So this value can be written as 0 is equal to 0.01 divided by xb squared minus 1. So 0.01 divided by xb squared minus 1 equal to 0. So in this case 0.01 minus xb squared equal to 0. Rearrange this expression. From this minus xb squared is equal to minus 0.01. Why? Because this is this side plus 1, this side comes to this side minus. Minus minus are cancelled. Finally xb squared is equal to 0.01. xb mean root of that is 0.01 is equal to 0.1. So finally xb value is 0.1. Answer range is given 0.09 to 0.11. So our answer is within this range. So objective of this question to determine the xb value, that minimize the recycle rate. Okay. So this xb is equal to 0.1, this answer within this range. So the mole fraction value, so this mole fraction xb value equal to 0.1. Okay. For further related videos you can like, share and subscribe my channel. Thank you.